Hello, good morning, everyone. Welcome to this Nmrg meeting. This is the second session that we have this week. Yesterday, we have the first session. Yesterday, we were talking about mainly on intent-based networking and the some kind of a report about Nmrg and the future of the group itself. Today, we are gonna concentrate the presentations on the use of artificial intelligence for network management. This session has been organized after a call for participations that we send along, of course, the Nmrg mailing list, but also together with other mailing lists in other communities as well. The approach behind this session is that we wanted to revisit, let's say, artificial intelligence techniques and solutions to observe whether they can be used for network management. This is not something new because network management has been already observed from the artificial intelligence perspective, but the area itself matured along the years, and then it's a good time to check whether artificial intelligence techniques and solutions could be used for network management in this, let's say, new context. Okay. So, of course, this is the note well. Blue sheets are already being circulated. So we have some online resources, of course. Then we have the agenda, materials for the presentations that we have today, as well as the remote participation. We have already volunteered 2 guys in the audience to be the minute takers and as well as the Jabber room. So as I mentioned before, this is the special session on the use of artificial intelligence for network management. And then we have organized the presentation in, let's say, 2 internal sessions. First, we're gonna see a set of presentations. Then we have some questions and answers. So this is 2B. And then 2C with additional presentations. And then in 2D, we're going to have some discussions, conclusions, and plans for the future. Okay. As I mentioned before, we wanted to revisit the use of artificial intelligence. This statements has been collected from the open call for participations. So revisiting AI for network management seems to be timely and more appropriate for this time. So we're gonna see now use cases and research results so far. And then emerging landscape for AI networks. Let me see. If it doesn't work, then you ask me next slide and I'll do it.
So, thank you. So I will start by motivating a little bit this work. I don't think that I need to explain why machine learning is relevant for networking. I think that more or less everybody can agree on that. But the thing is that it is working. Okay, now it's better. But I would like to in this talk, I would like to talk about. Okay, we can agree that machine learning techniques are useful for networking, but then we have several questions. For instance, which kind of machine learning techniques, which are the applications, or how we can apply it. And in our work, I will try to show at least one of these applications quite specific. So the idea is to use these deep reinforcement learning techniques. So deep reinforcement learning is, let's say, somehow a very recent breakthrough that we can claim that it was invented by Google through this paper in 2015, where they managed to train an agent to play a video game. So the idea in this case was that you have an agent, which is, you are trying to teach it how to play a video game. The agent will see the video game as the state, okay? And it will act upon this state through several actions. In this case, it has 3 different actions, right? Go left, right, and straight. And the idea is that the agent will, at the beginning, try the actions, let's say randomly, like a human that does not understand anything, and it will understand how the actions impact the environment, okay? So if I move right, what happens? If I move left, what happens? And so on. And after a while, it will understand which is the relation between the actions and the state. And the idea is that the agent has a goal, which is optimize the reward, okay? So what Google showed in this paper is that you can actually train an agent to understand which is the right set of actions so that in the long term, it maximizes the reward, which means that learns how to play this video game. So we're trying to do exactly the same to networking, which is, let's say, a little bit straightforward. In our case, the network is the environment, okay? And then the actions is change something upon the network. We need to change like the routing configuration, or you need to change the serving function path, or you need to change something out your network. Then out of this system, when you change something, you will receive 2 signals. The first one is the state. This means that when you change something on the network, something will change, right? So you can understand the state as, and this is a very broad statement, many different answers are valid, but let's say that you can think as the state of the network as the traffic, which is the current traffic load, and which is the performance that my network is providing me out of this network configuration and state. And then you have the reward. The reward is the target performance of the network, right? So the reward is how, well, more than the target performance, how far away I am from the target performance that the administrator has set, okay? So you can train an agent to do that, and let's say it should work. So I'm going to skip this because I don't have too much time, but let me explain then which was our experiment, which I have to say that it is a work in progress. We have a paper, and it will be updated with new results. So the idea is that you have one of these deep reinforcement learning agents, and we can change the routing configuration. And for this, and in this scenario, we have assumed that the routing configuration is as simple as the weights of the links, pretty much like in OSPF. Not strictly speaking OSPF as the IETF protocol, but as a routing protocol that you set the weights and routing happens. Then which is the state? Okay, when the state is the traffic matrix. Okay, so in each step, we have a different traffic matrix. The traffic matrix can be actually the same as in the last step, but the idea is that in each step, the agent will see one traffic matrix. And which is the reward? The delay. Okay, depending for a particular traffic matrix and for a set of weights, what you will get is a certain reward, delay out of the network. Then, which is the reward function? So we want to train the agent to minimize delay. So the goal of the agent is to find the right set of weights for routing such that for that particular traffic matrix, the average delay is minimum. So we want to teach the agent how to route autonomously. There is a quite interesting discussion, at least I hope that you find it interesting, which is that the reward function is actually the network policy. It's exactly the same. So what we understand as the network policy, and yesterday we have a very interesting session about intent. So the reward function is the mathematical representation of the intent that you need to install on the agent so that the agent will operate the network following that policy. I'm going to jump a little bit over the methodology. It's also in the paper, but pretty much what we did was we compared the performance of this agent with a quite sophisticated optimization technique, a traditional optimization technique, which is called simulated annealing. And the idea was that, so in RL, what we do is we train the system with 100,000 steps, random steps. After training, for each traffic matrix, we ask the agent, okay, give me which is the optimal weight for this particular traffic matrix. And then we compare that with a simulated annealing, which is a traditional optimization technique, which is a search-based. And in this case, for annealing, we allow it to run for 1,000 steps. So we ask simulated annealing, okay, for this particular matrix, which is the optimal weights, and you can iterate 1,000 times. So you can test 1,000 different weights. So it's not a very, let's say, fair comparison with DRL, but well, it's enough as a benchmark. And in this slide, you can see how the agent learns. This is the traffic intensity, which goes well beyond 100, because we wanted to test also what happens when you have a network which is very saturated, that it is losing a lot of packets. And here you have the average delay. And each box plot represents how many training steps we allow the agent to have. So when you have 2,000, you get worse performance than when you have 1,000. So this shows that the agent is learning. And you can see this very common exponential decay that is very common in machine learning. So the more training you get, the better results you have until you hit a flat curve. And this is the performance result with respect to simulated annealing. So it's the same, but here we see for each traffic matrix, which is the delay that each technique achieves. And as you can see, both results are quite comparable. They achieve similar performance. Still, annealing works a little bit better, and we want to tune a little bit the agent to perform better. But it is also true that for annealing, so for each traffic mapping, annealing has 1,000 steps to optimize, while the agent has only one. Okay, so from that point onwards on the presentation, what I would like to discuss is at least what I have learned and which are my conclusions regarding the use of deep reinforcement learning techniques in networking. So I have tried to make these slides as general as possible and not strictly related to my work. DRL, they have amazing advantage in our area. That's at least my opinion. It's quite an amazing technology. So on the one hand, it does not require any kind of prior knowledge of the network. You don't have to explain it. I have this amount of routers. The capacity of the links is this one. Nothing, because it understands the system as a black box where you have actions and you get a reward. That's it. So that's quite amazing. It works online and in real time, so you can actually run it and expect real-time optimization of the system, something which is extremely hard to do with other kinds of techniques. And it is autonomously, not just for optimizing, but also for learning. It's not like supervised learning where you have to generate a data set. The agent will generate its own data set. You don't have to do anything. It will play around with your infrastructure for a while until it understands how it works, and then it will optimize it. So with respect to traditional optimization techniques, which is what we have today deployed, it provides a constant optimization time, which means that any kind of optimization technique typically has to iterate many times, trying to find which is the best one. In DRL, after training, it's just one step. That's why you can achieve constant time optimization. So it's model free. Typically for optimization, well, typically no, always in an optimization technique, you need to run it on top of an analytical model of a simulator, right? And then the analytical technique will search over many configurations using this analytical model or simulator to try to find which is the optimal one. That's not the case for DRL. You can make it learn directly on your infrastructure, which means that you don't need to simplify anything. It doesn't matter how complex your network is. And with enough layers, although this has to be confirmed, with a deep network, you should be able to learn it. And it's a black box optimization. So any kind of optimization is tailored to the problem that it is trying to optimize. So that's not the case for DRL. So if you want to change your optimization function, you just need to change the reward function, but not the algorithm. You have the same algorithm for different reward functions. And in a traditional optimization technique, typically what you do is that you tailor your algorithm to your optimization goals. Then, of course, it has many challenges, which I will also like to discuss. The first one is training. Okay, so yeah, it's very cool. So, but it's very hard to think that I will allow an agent to run my network during the exploration phase, where it has to learn, because it will hit actions randomly to learn what is happening with infrastructure, like a kid, right? So it has to understand how things work. So at the beginning, it will be a little bit harsh on your infrastructure. And probably you are not going to allow training to happen online. And that's a common issue, not for us, but for anyone willing to apply this kind of techniques. So what other people are doing is, well, you can train it on a simulator. That's something that you can do. And people are doing that in other areas. Then you lose some advantages. And then once you have the system trained, you put it online to work in the real network. Another approach, which many people are doing, is to train it with an expert. So you take the agent and you show it how an expert is, which are the actions that an expert is performing in order to optimize the network. Then the agent will learn, okay, those are the right set of actions. And when it has learned these actions, you can put it online. And that's a quite common approach. And the expert can be either a human or can be another algorithm that you rely on and you believe it's an expert. For instance, a traditional optimization technique. Then there is a second challenge, and that's I will say a little bit more conceptual, but I will say it's bigger, which is the lack of explainability. So yeah, deep neural networks are very cool. My students are very happy working with it, but at the end, what you get is a black box. It's something that you don't know how it works. You cannot open it, or if you can open it, you cannot understand it. And you don't know when it will work, and you don't know when it will fail, and you don't know why it is working. And although academically that's not an issue, I understand that from the industry perspective, that's a big issue, because you cannot, it won't be able to offer you any guarantees, and it won't be able to offer you any kind of troubleshooting. If it breaks, you don't know why it is not working, and you don't know how to fix it beyond train it more. And that's, I understand, for the industry perspective, a big issue, also in terms of liabilities and so on. And again, that's not an issue just for us. It's an issue for anyone using this kind of techniques. So what a possible solution, well, you can always train more, and that's it. That's the solution. And another solution is that many people are starting to do something which is called explainable artificial intelligence. And the idea is that they use a second neural network that they connect to the first one, and the second neural network is used to try to understand how the first one is working and why it is working that way. And once you start understanding it, then you can start relying on it. And you have a very nice paper here, which, if you're interested, you can check. Okay, then the reward function. So I was discussing this at the beginning. So the reward function is like literally the network policy. So yesterday we were discussing the intent language. So in this case, what you need to do is, so let's say that you have an intent language, you compile it, and you render it into a reward function, which is the mathematical representation of your intent language. Once you have done that, you install it on your agent, and then the agent should be able to operate following that policy. So I believe that that's well, hopefully you find it relevant for this working group, for this research group. But this makes me ask myself some questions for which I don't have an answer. That's why we call it research working group, I guess. The first one is, can we actually represent any network policy with these functions? I don't know, because those functions have some constraints. For instance, they are continuous and so on. I don't have an answer for that. But this is an important question. If we are willing to go that path, we need to understand if this reward function can represent any kind of network policy. And then, okay, how we can compile this intent language into these reward functions. So as a summary, and I'm going very quick, so I really believe that this is an amazing technology. It is, to me at least, it really represents the full realization of an autonomous intelligent network, which is something that we have been discussing a lot in the past. And to me, this is how I understand this kind of autonomous intelligent system. But it comes, and it has many advantages: real-time operation, plug and play, no configuration, just pick a reward function. But it comes with important challenges. So the first one is training. That online training, it's challenging. And the second one is that it doesn't offer any guarantees. And here you have the paper, the code, the data set, everything. It's up there. Thank you.
Questions?
Yeah.
Very quickly.
Questions. There's a question from the Java room. The question is, have you tested your DRL model against adversarial agents?
Against?
Adversarial agents.
No, so far we just have tested it against a very traditional optimization technique.
Hi, this is Alex Clem. I have a question as well. Can you explain a little bit basically the reward function, how it relates to the policy? I did not quite get that part, because reward function would presumably have to be something that is quantifiable. And,
yeah.
So I'm wondering basically, how is policy quantifiable?
Yeah. So the reward function is a continuous function, which you can understand it that the output is a scalar value. So the higher is the reward, the agent is trying to find or is trying to act to find to increase always this value. Okay, so the higher is the better. So the reward function should be which is the distance between, in a mathematical terms, which I don't know how to do that, but the distance between the current performance of your network with the one that you are trying to achieve. And the distance is somehow the reward. I don't know if I was very clear. Maybe we can discuss that offline. Yeah, sorry.
Okay, thank you. Thank you for your good presentation. I want to ask, do you consider the multiple agent? Because if we simulate network, there are multiple entity, multiple router, multiple server. So I guess that you think about a single agent. So it is more proper to SDN cases. But if we reflect the real network infrastructure, is it more better to consider multiple agent?
Vertical agent.
Yeah, multiple agent.
Yes. Or virtual. Vertical or virtual?
Multiple.
Vertical.
Yeah.
So we only did one agent on top of an SDN controller, finding the optimal configuration for a single network. No, no vertical agent, anything else. We just one. And I don't, for this scenario, I don't see why we need more than one.
Chitogan, regarding the routing algorithm, is that what kind of routing are you?
So what we're doing
is it like a deterministic or?
It's deterministic. So
okay.
Let me elaborate. So another limitation of this kind of agents is that the action space cannot be very large. So the output of the agent cannot be, okay, give me the CLI configuration for all my nodes. It has to represent like levers, like in a video game, right? So a few levers that represent how you steer your network. So in this case, the agent was choosing the weights of the links, similar to our OSPF.
I guess I rephrase my question is that actually, is that linked to any kind of routing algorithm, or is that working for any kind of routing algorithm?
So we are trying to express an algorithm where you pick the weights of the links, and then each router will pick the path with the less weight, which is to me somehow OSPF. It's
yeah.
Okay.
Okay, we need to move on to the next presentation, but after a while we'll have time to come back to these discussions.
Thank you. Hello. Good morning, everyone. Shen Yan from Huawei. Today I will share our research program use CVAE in QoS management. The CVAE is one of the popular generative models and have achieved a great success in the AI area. The character is it can extract the hidden figure from the training set data and then reconstruct the distribution model of the focused object. Look at these 24 faces. These faces are not real. They are generated by the CVAE models. If we input the label, such as we want a female or male, we want an adult or children, and then the CVAE can generate the virtual faces for us. And why we and here we want to introduce this conditional variational autoencoder into network management to provide inference ability for the QoS performance. This is our basic thought. We think that the network is a complex system, and the QoS parameters have some hidden statistic data, which is hard to express by the simple distribution formulas or the combination of the distribution formulas. Therefore, we can use the CVAE to model the network QoS, and then we can use the trained model to generate the new samples, and finally we reconstruct the QoS distribution according to the generated samples. That is always should be a pointer. So that is, we input a condition like we want a female, we want a busy time QoS description to the CVAE models, and then it can generate a distribution of the QoS parameters, and then we can do some actions such as we can implement the proactive operations to reserve the bandwidth or the priority settings or migrate the flow of refocused. Or other application is we can evaluate the actions that if we migrate a flow or a VPN siting to a new path, we will perform well enough for our SLA. Okay. This is our plan, but I prefer to close the black box as this looks more simple. Here we focus on the QoS variation that's caused by the traffic, such as we pay more attention on the queuing delay than the transmission delay. So here we use the traffic metrics as the label, or say it is the condition of the CVAD model, and then we use the QoS as the value, like this. The end-to-end delay may be 10.2, and we set the label as 1, and then we can got the training process, and then we obtain the CVAE model, and after we got the model, we can infer the QoS distribution by input the traffic metrics as the label or as the condition, and then it will generate the QoS metric samples for us, and then we can use these samples to create the QoS distribution in any conditions. Here we have simple cases. It's a demo experiment that we set up a 9 traffic label from 1 to 9, and we set a hidden rules that the QoS label is the QoS label is a normal distribution, obey the normal distribution by the mean value of label multiple 10, and the variance is 3. Like this, we have this distribution of the probability distribution of the QoS parameters. It is virtual. We generate it, and then we use 1,000 sample to train the CVAE models, and it will take about 200 seconds per training time. After we got the CVAE model, and we will test whether the model can rebuild the probability distribution for our training set. So we input the training label from 1 to 9, such as if we input the label 2, whether we expect the CVAE model can output a QoS distribution with the mean value of 20, and then the variance of 3. That's the result. For the non-label, we can obtain the accurate distribution. The gray is not very clear. The gray curve and the gray bar here is the cases or the samples that we generated, and the red one is the cases, the samples the CVAE model generated for us. We can see that it looks similar. The arrow of mean standard and the 19 point is like this. So that is not a very important one, because many AI models can do that. So the interesting one is if we input a label that never appear in the training set, can CVAE build up the same distribution or our expect distribution for us? Such as here we have got the CVAE model, and then we input the label 11, which is never appeared in the training set, and then whether we can got the distribution of the mean value with 110, and the variance is 3. The answer is yes. For the non-label, we can also obtain the accurate distribution. So here it is a label 11 to 14. That's very important. Somebody may say, hey Jensen, your distribution is too simple, and you have only two parameters, and one of it is fixed. But for the it is based on the knowledge of human brain. That because the machine cannot know what is the concept of the normal distribution. We know that, but the machine do not know that. They can build up the model and recover the distribution from the training set. Okay, this model required new maybe new measurement technologies to feed, such as we need more high frequency and accuracy data, and then to feed up this model. And also we will face to the data expression and the transmission problems. Now we have two modes for the CVE training. The first one is path mode, which means that we train the model, CVE model, for each path as a unit, such like this one. So in this cases, we need to build up the path set based on the route. That is we are working on now, and our destination is we want to build up the CVE mode for each the CVE mode for each node. Like this, it is still in a challenge. If we can do that, we can combine each of the node as a path QoS distribution. But now we cannot simply add two or multiple node QoS distribution into one because it's not reasonable in math. So why we use CVE mode? Why not use other mode? There are some advantages. The first one is it performs quite well for non-distribution and better than the competitors. One of the competitors in AI area is the GANs. This is also a powerful tool for the generative model. But after many experiments, we found that the GANs performance not very good in our scenarios. So we choose CVE. And the second one and the most important one is the CVE model can infer the unknown cases for the mode, which is the few of the existing tools can do this. And the third one is the CVE can cover some complex problem we will meet in the network. Now we are using this CVE mode to predict and infer the QoS in given conditions, and such as we can proactively avoid the bad performance when the burst come. We can predict the QoS by the input the given conditions. And another uses is we use the QoS model to infer how and if for the simulation before we deploying TE policies. And in the future, we will try to use the real QoS data to train our mode, and we will try to explore the solution of the node model, the node mode, which is more. We think it is more powerful and useful in our problem. So here's a conclusion that CVE can use to model the network QoS, and the feasibility has been proved. And second one is CVE has many advantages, especially it can infer the unknown cases. And the third one is path mode is easier. We have implemented that. We will try to explore the solution for the node mode. It is still a challenge. And finally, we need new measurement technologies to support our data capturing. And here is some information for you. And welcome to subscribe IDNet. Thank you. Well, Professor, I have a
This is more
I have a a question for you, but you can
Should be the other way around.
yeah.
I think.
actually CVE mode can propose potential solutions for your deep reinforcement learning to solve the start problem.
The training.
Yeah.
Yeah, I agree. You can use these kind of things to train.
Yeah.
Yeah, I fully agree. My question is more a clarification. What you do is you predict what will be the QoS given the current traffic matrix.
Yeah.
So it's like a network simulator somehow.
Yeah.
Okay.
Okay.
Thanks.
That's
Okay, we need to move on to the next one,
Thank you.
and then we have the discussions afterwards. Jerome, you have a question?
No, my Jabber is down. I'm trying to get back. Is anyone in the Jabber? I don't know if there's any questions there. Okay.
Okay, so I'm Jerome. I will present some work that we have done on traffic analysis. I will not give any, or I will give very few details regarding the techniques. I will give more an overview of what we have done and what are the problems we are facing now. So as you can see, I put in parentheses encrypted because we are not only working on encrypted traffic, but you will see that there are some nice results and challenges that remain. Okay. So yes, regarding the challenge, okay, so traffic analysis is very important for a lot of stuff. Of course, for security, as mentioned in my title, you want to do some traffic analysis for detecting bad behaviors, for enforcing some access control. You may want to use for doing some QoS as well. And particularly, there is one topic, which is traffic classification, when you aim to label your traffic flows, with some, of course, labels and or profiles, which can be different depending on the context you target. It can be, for example, it can be the type of application which is used, maybe the user, maybe the type of the attack if you are in a security context, and so on. So it's a very diverse topic, and it really depends on the context. So when you look what has been done, I mean, in terms of, let's say, legacy technique, of course, for if you want to classify some application or type of application, port number could be used, at least in the past. For if you want to track some user, you can maybe use IP address. If you want to track some service, you can use maybe DNS name and so on. So this was kind of a standard technique in order to know what type of traffic or what it relates to. And of course, if you can maybe do some deep packet inspection or looking at the content of the packet in order to have a better view of what there is inside. Of course, it's the world that change, and many applications rely on the same framework, so it's very hard to distinguish them. Many of them are web-based, so meaning that they almost all use the same protocol, I mean, with some HTTP, HTTPS, and so on. Of course, we are all using now cloud, CDN, and so on, so IP addresses are not so very valid indicators of, for example, the origin of traffic. And of course, there is the problem with the encryption technique, okay, with the privacy concerns that raise more and more traffic is encrypted. So meaning that mainly today, it would be maybe a bit caricature, a lot of traffic is web-based and encrypted. So basically in HTTPS, and that's why we have applied a lot on HTTPS, our work. So yes, of course, that's good to have encryption. I mean, for user, in terms of protecting, in particular, your privacy. But then somehow it's also legitimate if you do some network operation to know what type of traffic is going on in order to do some operation. So there is this kind of need, in particular for security. If you want to apply some security policy, you need a bit to know what happens. And then somehow you don't need to break, and you should not break the user privacy. A lot of solutions today just rely on HTTPS proxy or in the middle in many companies and so on, which I think is not good. And so the question is, can we do some directly in first work we have done, can we do some monitoring on the HTTPS without, of course, decrypting what there is inside? So this is the first example, and very rapidly I will show you because I presented this example in a previous Nmrg session. So the idea is that, okay, there are different kind of things you can do. You can try to, if you look at web, you can try to look at what is a web page which is loaded, which is called basically a website fingerprinting. A lot of work I've done try to categorize the traffic. Is it, for example, web? Is it peer-to-peer? Is it voice over IP and so on? And we are in the middle where we try basically to know what is a service which is used. So basically we need to know the service provider. We have a multi-layer classifier. We first try to know what is a service provider, like is it Google, is it Dropbox, is it Facebook and so on, and then the different services that are behind. So we build one classifier for each service provider. We use a simple, or let's say simple or very, let's say regular decision tree algorithm to do that. And one main contribution was, if you look into the literature, most of the features that we use are pretty much the same. And we extended a bit. Rather than looking at, for example, packet size, we just extract the encrypted payload and we apply some statistic on the encrypted payload. And actually, this gives better results. Here, you have very rapidly some results. And as you can show here, we look for each service provider in which range of correct classification we are. And mainly for 51 out of 68 service provider, we have a classification. So we are really able to know what is the service I use for this provider without decrypting what is the traffic, with an accuracy around 95%. Okay, I will not enter too much into the detail. So then the question also that can raise is there is no encryption, is it so easy? You could say that if we don't have encryption, things are easy. Looking at this example, so basically here we use our darknet or dark space, in darknet instance on dark space, not dark web, where we have a 20/20 network that only used for that. We should not receive any traffic on that. And as you can see on the left pictures, here all the packets we receive in a short interval of time, where you have two square. One is the origin with IP address and port, and the other is the destination, also with IP address and ports. And what we know is that all this traffic is illegitimate on left, but we don't know what there is really inside. We know that there is probably DDoS, there is a scanning and so on. And what we want to achieve is to have the right side figure where we basically have the different kind of slices which represent the scanning, TCP scan we have on the darknet. And to do that, we try with some, let's say, on-the-shelf tools like Suricata. And we were not really satisfied with the result. We have still many components, and we use another technique. So its traffic is not encrypted, but the problem is that we should not, of course, analyze individual packets, but we should correct them in order to find the right pattern. So even if it's not encrypted, it's not so simple. So we use TDA, which is topological data analysis. We only use one part of the TDA here. We are now a bit further. What was the mapper, which is really the first step, which is basically, you can see that as a partition-based clustering. So we have a big space of data, multidimensional data, and then we compose few, let's say, hypercube in that, and we are this intermediate representation that we built in the middle, which is based on kind of clustering, and then we merge all the results together. Maybe you can discuss more if you want more detail about this technique, but with this technique, we have been able, of course, to be able to label a bit more the data we have in the darknet. Okay, going further, of course, I will give some feelings about the problem we try to address. Of course, the first question is always the same. We should target the right problem when you do some traffic analysis, traffic classification. So either you say that I want to classify everything, which will be very hard because I think you should be able to learn almost everything, and it's not very good because it means that you want to know what is everything as well. Or better for me, it's better as the second guess. It's maybe simpler because you prefer to build signature for particular, for example, use cases or profiles you want to be able to detect, for instance, if you think about security. And this is more compliant if you are a bit against mass surveillance because you don't want to track, for example, an individual user, but maybe you want or any service usage, but only one service use that you want to track. Of course, you have to think if you can do your analysis on a single, let's say, data instance or multiple data instance. Like if you look at a single flow, if you want to correlate different flow together, I think the second technique is usually more efficient, but is more difficult to apply. I will then go a bit further. So then we have the methodology, which is very, I will not really go into this. It's very classical, so with training and so on. One thing that I want to point out is, as was already pointed out and in the mailing list as well, is that the feature engineering, I think, is in the core of the problem. Choosing the right feature, I mean, you can use the different algorithm. Many people just try a lot of algorithm without thinking first about maybe the second slide. Maybe first thinking about what how the algorithm really works. I think it's really important to know use, of course, algorithm like black box, but also features. So one thing which I think is very representative is when you do some distance metric. Many people just use algorithm on the shelf. They use distance metric on the shelf. For example, you can use Euclidean distance, but most of the time there is nonsense. Just looking, for example, at port number. If you look port number as numerical values, of course, you can do it. You can apply distance, you can compute a distance, but there is no meaning to compute a numerical or Euclidean distance between port numbers, for instance. We need something more advanced. Just to show you some work we have done so far here is we look again the darknet, and of course there is some semantic in sports. And the idea was not to automatically, we have also done that, the semantic of ports from knowledge, but to build our knowledge based on the attacker behavior. So we look at what an attacker basically scan consecutively in terms of ports, and we construct this kind of graph, and then with some community detection algorithm, we were able to see what are the port number which seems to be close, I mean in the mind of an attacker, which then we can use this information into our model for detecting the attacks.
John?
So
You have a question from the jobber room? Or
just,
later?
just have one slide and then
Sure.
it's done. So just to conclude, I really think that regarding the encrypted use case, based on our experience and what you can read in literature, I think if you target a well-precise problem, you can easily find a solution, can find algorithm features that could give you some reasonable good results. I don't think this is a problem. Of course, it's supposed that you are able to maintain a very precise database for different environments. So there is, of course, some things that you have to fit, and it's not so evident like that. What are remaining issues that most of the case we don't consider as adversarial behaviors? And what I want also to mention is that the thing, of course, is always evolving. We have new protocols, we have kind of optimized protocol. If you look at HTTP, and even if you have HTTPS, of course, on top, but you have HTTP too. So now things are more multiplexed, are compressed, and so on. So it's very difficult today that we can easily apply your technique, because before basically we have one flow and we try to label this flow. If I can do an analogy, today we have a big tunnel where we put everything in a tunnel. It's all the same application, all encrypted, it's multiplexing, session are reused, and so on. It's far more difficult that you can read in most of paper, actually, if you look with the new context. And I'm done.
Question from the jobber room about data sets. How balanced or imbalanced is your target class?
Oh, okay, so it depends because I presented different use cases. In first, the HTTPS use case, it's quite well balanced because we control or we collect the data set. Of course, for the for example, for the darknet, it's not so well balanced because of course, it's real data that we gather, so we cannot really control the different proportion.
Shin from Huawei. I have a question that you said that you need to collect the data both from the network and out of the network.
Yeah.
And my question is how you align these two types of data, because we need to build up the relationship between the internal data and outside data. Thank you.
Yeah, you're sure. I mentioned that I didn't really focus on that, but that's true that in cases where we want to analyze traffic, we need also some knowledge which is out of the network, and then it really depends on the case. Maybe to cite an example, for instance, we have this darknet space, and also we have also honeypots. So there are two different, I mean, both on network, but two different network space. For example, we are collecting what are the passwords which are used by the attackers when they try to connect to SSH to honeypot. And we can, for instance, if you look in our database, we can see that at some hosts there are some changes in the password which are used because they try to target some other devices, basically IoT devices at that time. And so you can see also the same change in the port which are targeted or in the darknet. And of course, it really depends on the context. It's a very complex and a very difficult question, and of course, it has to be taken as individual context question each time.
Dean, please wait. We are just giving the mic to Chao. Chao, you're online,
Hello?
please.
Hello? Yeah, please go to the page 9.
Yes, we can hear you.
Can you go to the page 9? Page 9.
Sorry, can you repeat, please?
Sorry, yeah.
Number 9.
We can see this table, so I can understand exactly which is your method. Is that the which canon is your method? Is the selector feature, and what's the meaning of the Nmrg feature for the accuracy?
So if I understand well, your question was regarding the features. So we have different set of features. I was very rapid on features. So classical feature has features that you extract from state of the art that has been used for HTTPS traffic, and then we have selected set of features then we have full features, which is state of the art features plus our new features on encrypted data. And then we have selected features, which is a selection among them. If I go back to one slide, I think. Okay. Okay, here you can see what are the selected feature, which the one appearing in bold are the ones that we added. The other has one from state of the art, which are the selected feature, which are basically based on information gain that we do this selection. And then, so what means the table is that for each line, we look at the number. So, for example, the first line is the number of service providers for which we were able to classify between 95 and 100% of the service which have been used, and so on. And then we have the different bins. And so, of course, the first line is the one most representative for the best classification, because it means that for if you use selected feature, 51 of service provider have been services of 51 of service provider have been classified with accuracy higher than 95%.
Dejan Bogdanovic. I want to ask you on what link speeds and what sample rates can you work with? Did you try, when you were doing traffic sampling at certain rates, how does your algorithm work? Or you have to be on a live tap and see all the traffic?
Sorry, can you repeat? You mean for time of execution?
Excuse me?
The question is regarding if you can apply online, right?
Well, yes, that's the idea, because
yeah, I think if you look at this particular algorithm, it's I would call near real time, because our initial goal was to build HTTPS firewall. So I think in terms of classification, it's very fast. So, but the problem is that we need to have the full HTTPS session. So it means that if you do a firewall, you cannot block the connection. You need to observe entirely and then block. So it's not really real time. That's why you call near real time. Yes.
okay, so it's more of a forensic tool.
Yeah, in that case, yes. And then, yeah, we did some experiment on if you can already profile it during the middle of the connection. It works a bit, but of course not as is best.
Okay, thank you.
Xavier Marjou, Orange. First, thank you for this presentation. I did not understand whether you use supervised learning, unsupervised learning, or both of them.
So for this one, it's supervised because we need to build signature. For the other work I rapidly present on TDA is totally unsupervised.
Thank you.
Kiriti Kompella. I have a comment for you, which is, as you're doing this stuff and saying how well you can classify based on not just the classical features, but all these other features, you're suggesting to people how they can hide their traffic better. So I can pad my packets so that they all look roughly the same size. I can adjust the inter-packet gap so that that information goes away. Just a comment.
Okay, thank you. Our next presentation will be online. Armen, if you hear us, please connect.
Can you hear me?
Yeah, we can hear you and see you.
Okay. Hi. So I will be presenting an yearly research we are doing in Bell Labs at Nokia on model-free resource management with reinforcement learning. So please go on to the next chart. Yeah. So the motivation is the following. So in the future hyper-connected society, we believe that we will have a major challenge in controlling and managing large networks. And you can have in mind an AI-enabled cloud hosted applications connected through 5G and interconnecting hundreds of thousands of IoT devices and end users. So in such a large network, traditional approaches to management will be challenged because they require a learning of a model in advance and then acting and reasoning on that model. While in such large and complex systems, it will be hard to learn in advance the model and maintain it, update it, because of the dynamics of this large system. And we are after a novel approach of the concept of learning in interaction, introduced and derived from reinforcement learning. So the idea here has been already presented by the first presenter. So let me go very quickly through the high-level concept here. So instead of building in advance the model, the management agent will generate actions on the environment, on the system, and will collect the feedback. And this feedback will be separated into two flows. The first one is the interpretation of a state. So it will need to define notion of a state of the environment, and it should also identify what is called a reward, so the goodness of the state. How good is the state from the given the objective of the management. So let me go to the next chart and to show how we instantiate this general schema, and we apply it to an elastic cloud-based application. So the high-level objective is to automatically learn optimal resource management policies with limited prior information and adapt it to changing environments. So we are experimenting with the cloud-based application, which receives a variable load, and it can scale up and down. Basically, it can add or remove virtual machines to adapt to the current load. So the reinforcement learning module will generate actions. So what are our actions here? It's adding or removing capacity, adding or removing virtual machines. And then in the beginning, it will generate kind of a random actions. And then it will receive the monitoring input. And we identify here the state as being a combination of the current workload and the current capacity. And the reward is provided as a desirability of this current state. And it, in fact, it reflects a compromise between the capacity. More you are using capacity, less is your reward. And in case you are violating an SLA in terms of response time, you are paying a penalty. So you are in a good shape if you are using low capacity and you are not violating your SLA. And to reason and to build the optimal policies, the algorithm will build so-called Q values and update these Q values, which are defined on pairs of state and actions. And basically, these Q values will be used afterwards to identify the highest Q value for a given state, so which will identify the best action to be executed in the given state. So let me go to some results on the next chart. Next chart, please. So some results we present here are basically reflecting the ways we can derive automatically the control decisions by maximizing the system efficiency. And yeah, we need to mention here that the system efficiency is defined as the sum of discounted rewards over the entire time horizon of your system. And here we are using minimal system information, no system model. The only thing we know about the system is its state and reward as defined previously. So we observe the capacity, current capacity, we observe the current response time and the workload. And the iterations, these closed loop iterations of the learning agent show that we have a convergence of the average system efficiency. And this is achieved by identifying the best trade-off between minimizing the allocated capacity and maximizing the customer responsiveness as the reward function is indicating. And on the next chart, then we show how the system can adapt to the changing environment. And to do that, we first fit a system model and analytically derive kind of optimal policies which maximize the current reward. So this time we build as precisely as possible a model which connects the inputs and the outputs of the system. Basically, it connects the workload and the response time. And as far as this model is precise and the system doesn't change, we can see that this model-based approach outperforms the reinforcement learning approach. But then we introduce a system change, and which can happen in a cloud environment because of many reasons, because of adding an additional tenant to cloud and sharing the resources, or because of variations in network bandwidth capacity, and etc., which makes this precise model invalid or imprecise. And what we observe is that reinforcement learning continues to learn this change and strives to maintain the average return at a higher level, while the model-based approach is losing its performance indicator. Yeah, this leads me to the conclusion slide. The next one, please. So what we this initial research done in this initial research is that we elaborated some principles for state and reward definition. In some prior works, the state definitions have been done in a way that do not respect the separation of causes from effects. So if you look the way we define the state, it includes only kind of independent attributes, workload and capacity, which lead to the response time, which cause the state of the value of the response time. So in the past, some other works were including the response time in the notion of the state. So it's important to define a state in a way that it captures some independent dimensions of the system. And then the design of minimum reward is very important. So it makes sense to the engineer and it makes sense to the user of the system. And here we build a reward function which has a meaning. It is a revenue minus the cost. And in which case the return, which was the discounted sum of rewards, also has a meaning. It has a long-term profit. Then we have illustrated with some experimentations how the policies can be automatically derived. I didn't elaborate on that, but we have played with a real cloud system as well as with a simulator. And working with a simulator allows to overcome the real-time burden and accelerate the tests and have a quicker evaluation of algorithms. And then we confirm and validated this result within a real cloud infrastructure. And we've obtained this original intuition. We demonstrated that the reinforcement learning derived policies beat the system model-based approach under the changing infrastructure conditions. I will end with this short presentation with by enumerating a few open challenges we see in this area. So the first one is the unknown reward latency, because when you execute an action on the system, you cannot be sure that the effect of this action is seen immediately in the next iteration of your algorithm. So you do not know how long time, how is the inertia of the system is operating. So how long time it will take until the effect of your action it will be observed. This can be an annoying issue because you are learning on the immediate reward. Another problem we've been faced is the failed actions. Not all the scaling actions you execute on your system can be really executed. So your algorithm should be adapted in a way to differentiate between successful actions from which you observe your reward, and the algorithm should learn whether these actions were improving or not the reward, and the actions which didn't succeed just from system perspective. They just didn't manage to be executed within the system. So they will introduce the noise in that case. Of course, general problem well known is a slow convergence, the cold start. So some approaches should be put in place to accelerate this by probably introducing some domain knowledge. And the last point I would like to emphasize here is the abnormal environmental changes. So I mentioned here that when the environment changes, the reinforcement learning algorithm can deal with that and can adapt. But what if these changes are situations which are happening very rare? So you don't really want to learn on them because they will not have a sufficient time horizon to lead your algorithm to convergence. So you would like basically to ignore these situations which are failure situations, so that your policies are not kind of too much conservative. They can differentiate these normal operational changes from anomalies and failures. So let me stop here. Thank you.
Hi, Dejan Bogdanovic. I apologize. On what topologies did you test your model?
We tested with relatively simple web applications where you have load balancers and many workers beyond the load balancers and working in parallel. So you add and remove virtual machines by simply adding and removing capacity.
I haven't read the draft, so I don't know, but I would be curious to see more information about that, because the abnormal environmental changes are, really depending on what topologies you have, and then what actions were you able to take.
This is the point. In fact, the abnormal changes, like if you are running OpenStack Cloud, you can have OpenStack problems, right? Yeah, your cloud environment just can be in a abnormal situation. You don't want to learn which policies to apply from scaling perspective when you are in this abnormal situation. You want to tackle this abnormal situation by some specific actions you know, and not learn it. what you do, what you want to learn is when the system is operating normally, it will have variable conditions. So you want to adapt to those, but not learning directly the fault situations. I don't know if I managed to answer the question.
Balázs Lengyel Ericsson. Two questions. You mentioned slow convergence. Can you give us a feeling what slow means? Seconds, minutes? And how do you know that the traffic situation doesn't change faster than your convergence, actually, and that might lead to no convergence at all?
You have no guarantee about that. But if you go to the slide, the previous slide, I can comment a bit more. And the one before, please. Yeah, so the workload we've considered is a kind of a variable workload. Indeed, you can challenge the system by providing really a workload which changes the patterns all the time. So if you should assume that you will converge to a stationarity, to converge to some optimal policies under some stationarity assumptions. If your input load is not stationary, doesn't have any repeated pattern, it will be no. You don't have any guarantee to converge to anything. And maybe another answer also is that the underlying assumption is that your system is behaving like a Markovian model. So your workload variations. Your state definition should be done in a way that your workload variations are still preserving this Markovian property. If they do not, then you cannot claim any convergence. So in this particular case, we had a pattern of daily patterns. In fact, what you see on the left is daily patterns of variable workload. And it so you have, I think, 1 week of data or a bit more, and the convergence took about 1 or 2 days to converge to the right policy.
Thank you.
Okay, there are no more questions. Thank you, Armen, for presenting in the middle of the night. Thank you. Goodbye.
So this is, it's a summary of a project that is about to finish. That is Cognet. Cognet is our idea was to build a network management environment that should be based on, in general, modern machine learning. It's used machine learning, but the idea is to use any kind of data-intensive techniques to apply machine learning. Basically, it has been since it has been funded by the European Commission under the 5G PPP program, is very much oriented to 5G use cases. So the idea is that we wanted to experiment with different potential techniques, not only not to apply one, but the idea was to experiment with the different potential techniques and being able to build a framework that would allow us to select the best learned or trained approach and apply, these two, and we have applied it to some cases like, traffic identification precisely, resource management, and end-to-end service management. And in general, apart from that, there has been another applications related to automated cars and IoT. Well, for sure, it's based on open source and is about that to contribute to several communities. This should be a little bit more colorful, but this was I can tell you this was light blue and then a dark blue, and it's difficult to see. But basically, what we have here is the usual closed loop environment for control, in which what you have is a set of policies and a data stream that is generated by monitoring the interface and the functions that are running. What Cognos does, what Cognos does is precisely try to add a second closed loop, in which what you have is a data stream and a set of score related precisely to the policy engine. Yes, you should read here policy engine. Try here because it says so. And I hope that in the version that is in the portal it will be better. If not, we have to talk.
Yeah, we try to see. This is the automatic transformation.
Oh, well, then I'll send you a better PDF. So, so the idea is that adding this, the idea is that we have in the position of making some selection of the different trained results. So in more detail, basically this is the same diagram at the beginning, but with a little bit more of detail. And the idea is that precisely that zone over there is where several different mechanisms for machine learning, several different mechanisms for training the policy engine are applied with data sets that are generated by collecting real-time data there. Two important notes is that what we have is, as I said before, is two control loops in which we have intersection at what we call the Cognos Smart Engine. That is where we are applying the machine learning mechanisms. And second is that we are assuming that the underlying infrastructure is based on NFV plus SDN and a particular architecture in which what you have is a double SDN controller, one acting at the VNF level, the other one acting at the infrastructure level. So you can apply SDN rules for to control the behavior of the different functions. This goes in more detail again, so you can see here over there where we are assuming that there are the two SDN controllers. One, it would be here, the other one would be here. This would be controlling how the different VNFs are interconnected. The other one is controlling the behavior of the VNF themselves. Both of them are collecting data together with data related to the status of the infrastructure and data collected by the VNFs themselves that are processed and input to the upper loop, where the trained behavior is evaluated and then selected and fed into the policy engine that takes the decisions on network management. The current implementation that is available in several cloud deployments uses open source, use a set of databases to forward the different streams. It uses several tools for applying the machine learning processes. Is using a policy engine. Is using Open Daylight for as tenant controller. Open source Mano for NFV orchestration, and well, we are using OpenNFV Brahmaputra that is a little bit back because we started 2 years ago and we decided not to make many changes to the infrastructure itself. And well, just as a note, we are using SUPA for policy definitions for all the exchanges. Apart from this, and this is something that is running, and we will run a final demo. Well, in a couple of weeks, we are going to go to Paris to set up the final demo precisely. I mean, not to Paris, to the real Paris, not to Paris. And is it the Orange Gardens? Where we are going to have the meeting. And apart from that, as a side byproduct, we found that training models and using those data sets, I mean, initial data sets for training the models were extremely complex because there were a horrible lack of data sets. Getting data set is extremely complex because first, data is considered an asset, and it's considered more and more an asset, and getting significant data is almost impossible, even internally in the same organization. Can tell you, in an operator like Telefonica, getting real operational data is a real nightmare because nobody wants to disclose that. Second, there are important privacy concerns. There's a lot of concerns about that you will be exposing, and well, with the new GDPR here in Europe, no, they are in Europe, sorry. It will be almost completely impossible because any single data can be considered as personal. And third, even when you have the data, when you manage to get the data and you manage to anonymize it, etc., in many cases it's unusable for certain real scenarios because you don't have any clue about what's going on. It's true that with the deep learning processes and the like, you don't need to rely on them, but then making validation and making the testing of the trained data sets, unless you are bold enough to put them on the real network, is very complicated. And again, if you're running in an operator environment, telling the guys who are running the operations, say, no, I'm gonna put managing a piece of things that I've learned from some data, whatever, controlling the network. Try it and wait a couple of 100 years till you get the permission. So we started to work in the production of sound synthetic data sets. We started something that we call the mouse world. The idea basically is that it's a laboratory for generating synthetic data. The idea is to generate traffic samples in a controlled way and allowing that we can mix real and synthesized data. For example, is injecting real data mixed with a security attack, real data mixed with a viral event on the internet, things like that. So we are in the position of generating realistic scenarios and use them to train and validate the training. This is something that, as I told you, is a byproduct of the Connect project right now, but we are really willing to explore this in the future with the idea of producing something that is, I think, is very important for all this to happen, that is open data sets and even open synthesizing tools. So experiments and results can be replicated. And just to finish, this is something that, well, is a conclusion about that the data-driven in general, not necessarily machine learning, AI, whatever. Anything that is based on evidence from data is, we believe, that the next natural step in network management. But as I said, it's not only machine learning or AI. We had to apply, for example, a sensible way of managing the data sets. And well, still there are challenges before we see this happening in a real environment, operational environment. We have, first of all, that the networks are different in the behavior that from the fields that AI has been applied so far. It's not so static as, I don't know, dynamic image recognition or disease diagnostics and things like that. We desperately need data sets with are meaningful. And as Alberto was saying before, in these environments, you need to have always someone to blame. You have to understand what's going on. In a real environment, it's completely unapplicable to have something that you have just dropped and you don't know what's going to happen and why any problem happened. Well, that's all. And
Relay another question from the Jabber room. How big are those data sets?
What
big are these data sets?
Well, in general, what we register is a couple or 3 days of traffic. Big in terms of terabytes, we're talking about, in average, 1 to 2 terabytes, the ones we are generating right now.
Hi, so I have one question. In your architecture, did you decide that training is something that happens offline, and then you pick the model and you install it on your architecture, or it's online?
Initially, the initial training it happens offline, and afterwards the idea is that you keep feeding the data that you're generating and and you make it online. So it's let's say it's a double loop.
Before going on to the next part of the session, do the audience have comments about the presentations that we have so far as a group of them? Okay, please go ahead.
I am Chung Feng of China Telecom. You have mentioned several use cases which is very interesting. And
Can you speak up because
okay, I think that troubleshooting, especially for a virtualized network function, troubleshooting is very important. Should be also included in this use case for Cognet. Troubleshooting, yeah.
Troubleshooting, yeah, no, definitely. This is one of the cases that has been demonstrated precisely by the people from the Nokia team in Israel on something that they called, what is the name? To identify noisy neighbors and during the execution on network functions.
Okay, yeah. Thank you.
So are we gonna go to the second part of this session where we gonna have presentations that somehow summarize other AI-related efforts on, for example, standardization bodies or associations? Like the first one is gonna be on IEEE, then on ETSI, and then at the IETF itself.
Okay, thanks, Lisandro. So this talk is quite different from what we have seen before. It's not use cases or AI techniques. It's more I would say a new initiative in IEEE ComSoc, which are now called Emerging Technology Initiative. Before that, it was called subcommittee or committee. So this one is called Network Intelligence. Next slide, please. So as I say, it's kind of trying to build a new community initiative inside ComSoc, which is focused on the network intelligence. It's still not officially approved. This is in the process, but we are pending approval by the ComSoc ETC. It's not completely new. For those that are used to that or aware of that, it's inherits from the TCAC, Technical Committee on Autonomic Communication, which was established, I would say, several years ago. That was investigating autonomic communication. So there are a kind of legacy around that kind of technologies in the network intelligence. Currently, the mission that is defined for this ETI is essentially to support and endorse the research in the domain of artificial intelligence for software networks and towards future networks. So this is really not, the goal of the ETI is not to do the research itself, but it's to provide a framework to support the researchers in their publication of their research, emergence of community, providing venues for discussions. So also the evolution of networks towards more softwareized networks, as we say, will be also an opportunity for application of cognitive techniques and network intelligence. What we summarize as some enabling capabilities that we introduce with network intelligence is, of course, to increase the overall network operations towards faster deployment or faster processes, essentially going towards more minutes or seconds for those processes. Also to better handle the continuous provisioning. I mean, for legacy network, we used to have, okay, you plan, you design, you install, you deploy, then you operate, you have initial configuration, then you have reconfiguration. But more and more with the advent of softwareized networks, you want to go into a more continuous life cycle where configuration and reconfiguration is just the same approach, and you want to go into continuous provisioning. Also end-to-end orchestration to have current deployment of IT and network infrastructure together, such as with service change for NFV and SDN, and also the aspect of more reliable and availability of the networks. Okay. Yes, okay. This is some of the topics that are listed as topic of interest for this network intelligence ETI. I will not go through that. It's available. It will soon be available on the webpage of the ETI. But globally, we are targeting different kind of artificial intelligence techniques, machine learning techniques, but also the realm of autonomic networking and data analytics. So currently, the officers of this ETI are listed here. The chair is Nmrg Yaya from Orange Labs in France. Then Vice Chair Mohamed Fatenzani, which is from Montreal in Canada. Technical Program Chair Noor Al-Imam, which is also from Canada. Standard Liaison, I'm the Standard Liaison Officer, so that's why I'm doing this presentation here in IETF, IRTF. We are trying also to create a liaison with other groups in other standardization bodies. And Secretary Weverton Coderio. So participation to this ETI, for those that are not aware, you don't need to be a IEEE member to join this ETI. It's, I would say, a community of researchers. So anyone which is willing to participate to this community can join. You just ask the chairs. You will subscribe to the mailing list. And then you can even propose activities or events in this ETI, and you will be aware of what's happening. There are already some activities that are being planned or that will happen soon, organized by the people involved in this committee. So there will be a first international workshop on network intelligence co-located with the ICIN conference in February in Paris. You have the link to the workshop. The deadline is already over. Sorry. There will be a third international workshop on management of 5G networks, 5G MAN, which is has been organized usually with the NOMS and IM conferences. And the next one is in April in Taipei. The AI Nate conference next year, which is organized by UrProside, which will be co-located with the MPLS SDN-NFV conference in April in Paris. And we have some people attending IETF meetings that will go to that conference, so you will see some of those guys. There is also a special track on autonomic network management organized regularly with the IM and NOPS conferences. So this is also a topic where you can find researches on this aspect. Some standards area where members will try to get involved and active. So this very meeting, IETF and IRTF, but also you will see later a presentation on the ETSI and IEEE standard committees. And what we also have in the plan is to organize in the future special issues for various ComSoc journals and magazines. So please stay aware of that for the future. And that concludes my presentation. So this was just really to give you information about this new committee that is setting up. We are trying to also invite members to join this committee and to bridge the different communities and have more events, more time to discuss and exchange on this question of artificial intelligence for networking. Thank you.
So it's not this one. Yeah, thank you very much. So this is the other one.
Hello, everyone. This is Will Liu from Huawei. So today I will actually, I guess in last year or before last year, I presented some, topics about this work. At that moment, we just started this work, research on the network intelligence. And from last year to this year, we have made some progress. One of the biggest one is that we create a new ISG in SC called ENI, Experiential Network Intelligence. This ISG or this group is focusing on the network intelligence improvement and the migration. So actually, today's presentation is a joint presentation. John Stressner should be here to present some part of this presentation, but due to his health issue, he cannot be here, so I will present that part on behalf of him. And next. Okay. So in my presentation, I will basically present 3 parts. First part, I will talk about the progress of ENI. And the second part, actually, this is from John. It's about the MEF work. It's about the policy work in MEF. We will discuss the progress. And the third one is from one of my colleagues, as we are doing some technical work on how to development and how to implement such technologies to the real network. So we have a new use case and proposed as a draft in IETF. And this one is something we are doing in our optical network and help the optical network to collect data and to predict the healthy status of optical network. So this will be presented by my colleague online. So next, please. I can use this one. Yeah, okay. So this is the basic progress of our, of the ENI ISG. So this was established in the February of this year, and there are more than 15 companies joined as members already. And so the core idea of this work is I listed on the top here. So when we were proposing this work to SC, we meet a lot of challenges because the network intelligence is a very big idea. So it's hard to, limited the scope and to explain what's the detailed idea of this concept. So at that moment, we proposed these 3 key terms in this ISG to make people easier to understand what we are doing here. So first one is network perception analysis. So this one is that we collect the data from the data plane as well as the management plane, and we analyze and predict based on this data. And the second one is data-driven policy, meaning that actually we already have policy work in IETF as well as other SDOs such as MEF. But that policy is about predefined policy. It's that operators or the administrative management people predefine this policy and they put this policy into, for example, the management function controller. And so this data-driven policy is a little bit different. It's meaning that after we collect the data, we change or we create the policy based on this data, based on what we learned, what is happening in the network. And the third one is about AI-based closed loop. So the goal is to make use of the AI techniques to enable the closed loop so that we reduce the manual work in the management and the control of network. So these small words are what we are doing. Actually, it's detailed explanation of what I said just now. And so in the first phase, we will specify a set of use cases and architecture in the second phase, and about how to make this, these 3 key elements in the future. And so the figure here shows the progress. So after this ISG was founded in February, we set up 2 phases. The first phase we are focusing about the use case, requirement, and gap analysis. And the second phase we are focusing on the framework and the techniques and the practical requirement and other stuff that enable this techniques. So basically in this year, we have 4 meetings planned. We already have 3 of them. So the first 2 are held in the headquarters of SC, and the third one was held in Beijing. I guess some of attendees here have joined that one. That was hosted by China Telecom. And the fourth one will be held by Samsung in UK close to London. So next year, the meetings for next year are also planned. I will show you in the next page. And this figure and the other figure here shows the roles from different companies. So we have chairman, vice chairman from Huawei, from China Telecom and Verizon. And we also have some main players such as Samsung, Polya Telecom, SKT, Intel, and Chunghwa Telecom, blah, blah. So basically, because this ISG was founded this year, so there are also still many operators and vendors are in their progress to join us. So we also hope that you will be interested in this work and join us. So this listed the ongoing work in this ISG. So basically, we already started 4 work. They are use cases, requirement, gap analysis, and the terminology. And there is an upcoming work about the architecture, which was proposed by Verizon and will be started soon. And this is the page I just added because John is not here, so I want to talk a little bit more about the first part. So the use cases already received more than 14 use cases for both the wireline network as well as the mobile, the wireless network. So basically they can, I'm not going to go deep into this. So basically they can be summarized into 3 categories. So one is the resource management and optimization. The second is the service experience optimization and assurance. And the third one is fraud detection and prediction. So basically, people are, we see that the operators, they want this working group to help them to resolve these issues that it's not, dealt with very well in the existing network. For example, they still need many manual configuration and many manual decisions on this work. So they really, wanted such solutions come out from the industry. So this listed the ENI ecosystem because as we discussed that there are many organizations that are working on these directions. Actually, we are just one of them. And in SC, actually, we set up this ISG and we discussed with the board of SC. We wanted to make this ISG as the core group to make people, aligned and make people get the consensus on what is the concept of the network intelligence and what we are doing and what is the scope. So basically, the ENI will generate the concept, the mainstream use cases and the requirement, as well as the high-level framework. And the requirement for the interface and the protocol and the data models will be dealt by other organizations such as IETF, 3GPP. So we also have some colleagues working there to create some related work in Run 1 and Run 4. And in IETF, we have the data models here working on. And for the ITOT, we have the big data project in SG12 working on the data analysis and the KQI, KPI issue. And in MEF, John is leading the policy work there. And for the BBF and the JSMA, we also discussed with them and we want to make more cooperations with these organizations. And for the SDNIA, actually this is located in China. It's mainly, the main body is in China, but it's also regarded as an Asia organization on the SDN and NFV aliens. So they just founded a new group called AI applied for network. Basically, this can be regarded as an industry group for how operators can better use of these technologies. So so we wanted to cooperate with the mainstream players as well as the organizations, and we already sent out many licenses, including IETF, BBF, MEF, and many SGs in SC. So that's for the ecosystem. And this is what we see for the evolution of the near future about this network intelligence. So basically, the content here was drawn from the keynote speech from Mr. Wang Tao in UBBF in this year. So Mr. Wang Tao actually he is the boss of Huawei's development and management department, and so he have a speech on the network of intelligence this year in December, and so basically they have figured out the the stages for the network intelligence. The first one is automatic, meaning that you have the automation for the service distribution and for with the joint of the integration for the control plane. And the second step is adaptive, meaning that you can collect the data and you can meaning that you can analyze the data and you can improve the management based on that analyzed result. Actually, this concept is similar to what Diego just presented. So they share the similar idea. And for the third steps, actually, we think it's more like a future work. So we make it like the 2020. So that we can, well use the AI technology to largely reduce the manual configuration and the manual decisions in the network, meaning that the network can be run by itself, just like the self-driving cars, meaning that you have your intent input and the system in network can generate the policy and as well as the configurations itself and make even better decision than the human beings. So this is our next steps and as well as the agenda for the meetings, upcoming meetings. So all the, as I said, we welcome all the companies join us. And so actually we have online meetings almost every week. So we already have 20 plus meetings in this year, online and offline. So offline, actually, we have 4 per year, and online we have once per week. So this listed there is a link here. You can click and find all the meetings information. So I just listed the rest meetings. For the rest of these years. So from this month, we have these online meetings on each work items. And in December, we have the 4th meetings. And also we have a workshop joined by other organizations. And in next year, we already planned 2 meetings in the headquarters of SC. So next, as I said, next meeting will be in UK. Okay, so this is the first part. If there is no more question, I will go to the second part. Second part is about the progress of MEF. So because John is not here, I will briefly present this part on behalf of him. So as you might know, that MEF started policy work since last year. So they have so this is basically a summary of what they are doing. Actually, they are doing an extension of IETF SUPA framework, and they defined the declarative because as SUPA was founded in IETF, the declarative or intent part is not in the scope. So actually, they extended this and they do the declarative and intent policies in addition to these imperative policies in MEF. And they already have the information on the model used as a grammar about how to define these APIs and DSLs. And basically, they defined these three DSLs and with mappings to each other. They are imperative policy, declarative policy, as well as intent policy. Okay, I will go first. So I will skip this once, and let's go to the third part. So third part will be present. If you have any questions on the second part, please contact to John Stresson directly. So the third part is about the use case on the wavelength division service. So could you let?
Hello.
Xiaojian.
Okay. This is Xiaojian from Huawei. Yeah. Okay.
Yeah, you can go.
First, I will give a background.
Yeah, we can hear you.
WDM is a method of combining multiple signals on last beams at various infrared wavelengths for transmission along a fiber optic media. And a WDM system use a multiplexer as a transmitter to join the several signals together, and the demultiplexer as a receiver to split them apart. And during the wavelength division service running, the network data is consistently generated from the wavelength division device, and it can reflect the process of the service running. And the motivation of this draft has two meanings. The first one is in the case of traditional wavelength division service, custom is accustomed to handle the network failure after the service interruption. Such passive strategy is inefficient and easily leads to the long service interruption. And the second is this network data can help operator to judge the time point at which the service is abnormal or normal, or service is risky or healthy. And the goal has 3 points. The first one is illustrate the requirements of the network data used to evaluate the performance of wavelength division service. And the second is demonstrate the different application scenarios of network data in wavelength division service. And the last is present the existing problem of learning network data. Next slide, please. Okay. We summarize the network data. This has 3 attributes. The subject is an object to be measured, and it has multiple properties from different dimensions. And a subject may have one or more measured values, and each measured corresponds to a specific indicator. And each report of the measured value will have a time step attribute to indicate its time. Next, please. Okay, we'll give a use case. This might be 2 use cases. And the first one is alignment detection. Alignment detection is the identification of items, events, or observations which do not conform to an expected pattern or other items in data. Typically, the anonymous items will translate to some kind of problem, such as the optical layer problem. Okay. And for a wavelength division service scenario, network KPI data include the FEC-BF. This means the forward error correction coding before the error correction, and the input optical power, the last bias current, and the other key factors. This statistic data can be further used to detect wavelength division service alignment or improve the accuracy rate of for the wavelength division KPI alignment detection. And the second is the risk assessment. So this is a component aiming at providing a estimation of the overall network risk condition. So this is very similar to the previous use case, but risk assessment module's goal is to anticipate the network event, forecast the short-term change and the risk in the network. It it is based on the trend of network data. And there are two ways to access the network risk: the single KPI scoring and the multi KPI scoring. The single KPI scoring is use the score of a single KPI to access the network risk. Also, if the device or the service is monitored by several key KPI, the risk should be analyzed by the integration of these KPI scores. Next, please. Okay, we can see this single KPI. Yeah, we can research from different dimensions of a KPI. For example, the fluctuation, the trend, the threshold. It shows the statistical index which rise and falls sharply over a period of time, and indicates whether the state of the network element is stable. And second, the trend. The KPI data is connected according to the acquisition time, and the trend component can be obtained by decomposing the stored data. When the state of the network element is in the process of the deterioration, there will be a smooth process of change, resulting in a rising or falling trend. The threshold, we know the network element attribute itself defines the KPI threshold that it can maximum support. So, once the KPI value is smaller than the threshold, the closer of this value, the lower the reliability of the KPI. So we can see the left down figure. Okay, this is use a weighting process to weight the three dimension to the single one. Then we can see the right part is multi KPI. We use the two dimensions of a KPI analysis. So the corresponding the score calculated. Next please. Okay, this is an open issue. So so how to match the data from different time period. We know in the process of data connection, the connection period of the same KPI may be different from each other. For example, for multi-domain deployment service, there may be many different connection period for network devices, such as 30 seconds or the 5 minutes, 15 minutes, and so on. Sometimes the comparing is performed among these different domains. So we need to merge this data set from different period into integrated data set using the metric in the period, such as the mean value, peak value, or median value. So we are welcome you everyone to join this research topic. Thank you.
Okay, that's it. That's all about our presentation. Any questions?
Shen Yan, just for the comment, will you please turn to page the previous one? Yeah. Maybe I have the answer about your open issues. That is the question that I just asked the Germans, how to align the data from different scope. I think that it depends on your frequency of operations. For example, if you do operation once per second. That the higher frequency data will be helpful, will be unhelpful. It will be a noise, also useless. So it's the answer should be your depends on your frequency of your operation. That when you need a lower operation frequency, you do not need a more higher frequency data to feed your system. That's my my private opinions. So thank you. And another comments. I stand for SC NGP work item 6 idea, and said actually I'm a little bit surprised that there's somebody talk about SC works, and we are welcome to have any corporations based on our working scope, and we are focusing on the architecture, the protocols, the communication between different devices, and I think we have a lot of working point that can be cooperate and exchange our useful information. Thank you.
Yeah, thank you very much.
So we have our last presentation for this part of the meeting, and then we will try to save time to have an overall discussion and assessment of what we have learned today.
Thank you. This is Shane, Huawei. I will try to be a little bit short, then we can have enough time for discussing. This is summary for what we already have the efforts in IETF and IRTF. Actually, before that, we did have the Nmrg, so machine learning research group as proposed research group for almost 1.5 years. We did have some good discussion there, collecting use data, use cases. But given there are so many use cases in various area of network, we are fail for converging to certain use cases and reach the agreement what may be standardized. So here we are forming another effort. As most of you may already join the mailing list, IDNet mailing list. We actually had that mailing list to start from this April under IETF. And up to now, we already have more than 350 something. And we actually have more mailing lists discussing the Nmrg before. There are 45 active participants. This is a little bit analysis what may is there a light? Lighter? No.
Are you on the laser?
Yeah. Okay. This is a little bit analysis what the who is a participant in the mailing list. Oops. No,
I move on, you point with the laser.
Yeah. But the slides, I cannot control the slides. The first one. Go backward. Yeah. Okay. We actually saw a lot of people from universities. So far, we also have the vendors and ASPs. So far, we have very few participants from ISPs. But actually, we target both the ASP network and the ISP networks. And we saw a lot of participants from European and Asia, also North American, who's leading in AI areas. This gives a little bit reason. Everybody knows how important to apply AI into the network. It can make the network be less human and dependent. But actually, there's already a traditional way to make the network autonomic by using the if-else way. But in that way, that means actually the network devices itself may become more complicated because whatever the autonomic function you want to put in, you need to code that. Machine learning actually give us another opportunity, which may able to, have both autonomous and to reduce the complexity of the network devices. That means, we may be able to have some kind of unified algorithm, machine learning algorithm, to be able to handle multiple use cases. Because the algorithm itself can train itself to adapt into different scenarios in different conditions. So that gives us the possibility to reduce the complexity of network devices for do not to put too much efforts on use cases. This is the IDN architecture we already have abstract. In this we have 3 layers: infrastructure layer, control layer, and intelligence layer. We put in on all the machine learning and AI efforts to become a platform which can training from the various data we got from both user devices and through the measurement function from the network devices. They provide real-time data to the AI platform, but actually the data itself is, for now, is in very different format. So that's why we need data refiner here. Ideally, in the future, if more standardized work take on, the data from the network could be unified or somehow be formatly handled before it can become the input data into the AI platform. On the downstream, the AI platform will generate policies or the executable strategies. Then the control function will translate that into the very detailed indicating the network function could take on. And that whatever the network function change, that will influence to the network status, which will catch by the measurement function. I'll skip the use case because the use case already been introduced several times or mentioned by others. There are 2 use cases we already have the prototype and get successful results, traffic balance, and the proactive service level agreement maintenance. As I said, there are many high-value scenarios has been proposed, and there is one document already gathered those use cases together. But I would like to spend a little bit more time on how, what may be the standards point in the architecture. Actually, from this architecture, we can clearly say there are 2 aspects of it. One is the data aspect. From that's how we could get the data from different scenarios according to different targets and pre-handle them, pre-process them before as the input for the AI platform. Another, the control part also requires the policy to be formalized and to be able to understand by the controlling function and by the network devices. So all of those actually request the data and the policy as the output of the AI platform to be standardized. Otherwise, the devices, particularly the devices from different vendors, would not be able to function without modified. Okay, I already actually. This is actually my last slides. In this, I'm not going to going through the details, but in this, you can see there's a lot of use cases, and each use cases have different data request. And for the control aspects, the output for the specific scenarios task is actually also different. So that actually come to the discussion point I would like to call attention is we actually still struggling what could be standardized in these areas. There are two approaches for how we do the AI or machine learning in the network areas. First of all, the machine learning algorithm itself is algorithm, which happen in whatever in one within one network devices. So that's not be able to become standardized. The standardized is what happen on the wire for between devices or at least between functions. So there are two approaches for the data would be used by the machine learning functions. The first one is we could use the data whatever the current mechanism provides to us. That means collects the data from the current network devices. But those data are very different for their original purpose, and the format of them are variable, very different from each other. Given the different measurement mechanism and the different measurement frequency, the data may not be suitable for machine learning at all, particularly for those real-time machine learning tasks. Then there's another approach. We maybe re-examine the whole data set from the aspect of machine learning algorithm. What the tasks we would like to complete, and what the task lead for data as input. Then we can work back. What's the new data we need? What's the new measurement algorithm we need, and where the data collection and where the data should be translated into a centralized or maybe distributed place to do the AI calculation. Yeah, all those still in discussion. I don't have answer for now, and I believe most of you don't have answer for now. But I would like to see more discussing in both network machine learning research group mailing list and the IDNet mailing list. Yeah, there's one last point I would like to mention is, we are always thinking, where is the possible balance between the very specific use case and something could be abstract into calm along multiple use cases, because as standardization, we would like to get, as much as possible value from the standard format to be able to serve multiple tasks rather than go too deep for the very specific, very narrow use cases. But as you can see from this figure, is different scenarios, different tasks actually request very different data. So we're in the middle to find the best point for standardization. That's also another point we need to discuss. And the result of discussing will become very valuable input for IETF standardization. And we have to be ready with some level of result to be able to start another efforts for IETF working group. Okay. That's all for now.
Do you have comments on this presentation?
So Yong from Tsinghua University. So thanks, Shen. I think what the question you raised is quite important because as we know, there are a lot of state-of-art research on the machine learning. Excuse me. On the machine learning. So in addition to the network management, there are also studies on the TCP and the multimedia, and even the new NFA placement, some other areas. So we needed the data right for the machine learning, and we also needed some kind of control message to communicate between each other to set the parameters and also the result to the network entities. So I think this topic is quite important.
Thank you. Fully agree. We would like the data, and we would like the raw data as well. But for more than that, we would like the data with the right format to be able to use as the input for the machine learning. Yeah.
Just some comment about standardization. Nmrg is a research group, and then standardization is a nice outcome, but it's not the goal of the research group itself. So identify which can be standardized, but also identify which cannot be standardized or should not be standardized is also an important outcome. So because we become aware of it. So these were the presentations that we have today. The idea of this session is to bring together people that were working with AI for network management. As I mentioned in the beginning, we wanted to revisit it because the use of artificial intelligence for network management is not new per se. Probably more than 10 years, people have been working on that, but the AI area has matured along. And then we, as a research group, we are looking for directions for future work to be done in the context of the research group itself. Does the audience has opinion about it? What to move on? How to do next? And is it an area that is worthwhile doing that? Right.
Anyone willing to share his or her thoughts about what we have learned today? I mean, general comments about the use cases, what could be the requirements we need to tackle, what will be research items we would like to investigate in the research group. Just share your thoughts. It's a general discussion. We want to try to build a kind of roadmap for the research group, or maybe beyond the research group, of what we can achieve, what we need to work on.
Dear Lopez, Is just to insist in what I was trying to say during the presentation, is that an essential tool for research is precisely to have data available. I think that, and especially in the case of these technologies that are so dependent on what is the data you feed to them. And I think that having a set of open data sets that are well known, that are properly, and proper metadata. So whenever you report a result on a particular algorithm or a particular technique, you can refer to the data set you have been used, and these results can be reproduced and analyzed. Is essential if what we want is something apart from, hey, I have this magic here that has these nice results, and then try to repeat it. But if you don't put the right ingredients inside the concoction, it will not work. And this is something that...
I have a question with respect to that, because, it's a recurring comment or problem we are facing. I'm trying to sketch, in other domains, for instance, image recognition, there are, I would say, reference or standardized database, or in medicine, etc. Can we imagine a similar approach or similar databases for network or for specific function or problems in networks? Is it the right way to think, or is it completely different, and we should not seek to have reference databases, but to have maybe focus on use cases, and what are the properties of the data we expect to solve specific problems of networks?
I think that we have to, the goal should be similar, in my view, similar to what you have right now for biosciences, for example, or genoma or things like that. Probably different, because doesn't make any sense. The data sets I'm aware of have more than 20 years, the publicly available ones. And the traffic, the traffic that is reflected there is, is IP traffic. On the other hand, they are not following the current patterns. They don't have, for example, video flows. Just as an example. So probably the idea would be that we should have to keep those data banks, or whatever we call them, because it should be a set of data sets, and keep them updated according to the evolution of the network search patterns. I know that's challenging. It's and again, data is an asset, and it's complicated. That is, but that they become really widely shared. But at least having a set of not necessarily complete sets, but at least something that is usable and can help in reproducing results.
And this is Jefferson Aubrey. I think that learning for our past experience with ANIMA working group, maybe a good way to push this forward is to have use case aimed meeting, and as we can have, and all these use case should be in as an ideal word, they should have a draft, so we could discuss using the drafts previously read by the attendees. So we can discuss a minimum set of use cases and try to produce from the use cases written on the draft some more material in order to push forward the directions for the AI and the intelligence-defined networking.
Yeah, the use cases are very important. Actually, we already collect various use cases, both from the previous Nmrg meeting and also today here, particularly for network management. I think the group should go ahead to do the analysis research for those use cases. Try to find out, how those use cases could be come together and to do some kind of like gap analysis, what the use cases needed and the current network cannot provide, and what is missing to be better AI-ready network or network management. Then, based on that result, we can, somehow think where maybe the direction for future potential standardization work.
Chinogan from Telno. I second Diego mentioned the data is important, but also the methodology is important as well. I mean, the traffic classification. Different vendors have different implementation and use different classification, and that lead to a different insight. But very often we don't have the standard scheme to classify the traffic, like a type of traffic and also a protocol and sub-protocol, what kind of level we need to obtain the insight that we need for the management, which is very important basis, which I think is kind of missing. I saw some proposal to have a standard scheme, but benefit would be very good. I think if all people using the same classification and then we all have the same insight.
May I try to summarize what we have so far? And also I'm trying to remember what we have on the Nmrg in the past too. Because Diego mentioned about the data sets. And for example, in the past, we were able to, let's say, prove that get messages from SNMP was not used, given a set of data sets that were shared and collected from important backbones around the world. That same data sets shown that SNMP v3 was not used that much, although everybody was expecting that. So we have on the working group itself some experience on that, but we never used data sets for these artificial intelligence supports. So maybe we could try to do that again. And the problem with data sets is actually having people willing to provide the data so that we can collect them and share them somewhere. So the first is the infrastructure for sharing. Second is having the willingness to share the data set. Another aspect that Jefferson mentioned was that we have used study cases in the past so that we could evolve in the group. And then the fact that we need not only to check the case studies, but also we need to analyze them. So we should go one step further and analyze them. And then all of it, we should consider assuming more specific methodologies. Instead of having everybody doing their own way, maybe come up with some methodologies that could be reproducible. Please go ahead.
Hi, Lu Yuanfang, Expedia. I think we're all focusing on the right point on the data, but I don't see there is particular AI data. So we got all the data. You mentioned SNMP, and today SNMP is old. We still have to use it until new is all implemented. There's a young model, and there's open config. We actually prototype it, model it, demo it. You can get all real-time streaming. That's what you need. If you don't have real-time data, forget about it, right? Whatever when you use is 15 minutes ago, some time ago. So I believe all these are foundation work. It doesn't directly to do AI, but it's tightly coupled. Without them, you cannot do AI. So on top of that, you can do your AI in centralized approach, in distributed approach. One is the good data set that I think we all agreed. And two is the how to handle the massive data. Sometimes you can see you dump them into TSDB. Pulling out is also very difficult. Is that the right way to do it? There's an in-memory processing thing and all things. You need to scale it and to be able to process in time. For some, maybe for long-term study, training, some maybe just for immediate troubleshooting. So I think we may, in my mind, I don't think there's a particular AI data, but AI depend on all these data. If we have enough power like a machine, we can do that ourselves. We don't. So we need AI. We need all the algorithms and things. And the complexity in networking, or say the full stack, all the applications, e-commerce and so on, it's really different than like natural language, like image processing, speech recognition. All these are fixed set. These are distributed all over the place. So it's unsupervised learning a lot of the time because we don't have labeled data. Just my comment. Thank you.
Thank you.
This is Jefferson Aubrey. Just to add to my suggestion before, I think something that we should agree before is to have some kind of a minimum set of agreement on the use cases or the data sets in order to have some minimum requirements for the drafts and for the public data sets. And I think this we could do in the mailing list, just changing an opinion using, for example, the use cases that Cheng mentioned before that are sent to the intelligent defined networking mailing list. So, and this is something that also worked for the autonomous networking use case, because the use cases are at some sense they are comparable, because there is this this fixed set of sections and minimal information that is required to understand the use case.
So this is Albert. I would like to share my opinion on the data sets. I agree that data sets are the most important thing when you are training a machine learning algorithm, but I also agree with Diego. They are an asset. So although that in an ideal world, people will share them, maybe this is not going to happen, because my algorithms will be as good as my data. So why share it and have my competitors take advantage of that? And I'm from the academy, so I don't know, but I don't have too much hopes on that. But in any case, if you take a look to other areas like computer vision, public data sets typically are not used for training. That's not true. They are used for benchmark. Sorry? For testing, for benchmark. So I train my computer vision algorithm with my own private data, and then there are some public data sets where everybody goes and benchmarks the algorithm. So it's like a public benchmark. I am as good as, I don't know, I have a 92% accuracy with that public benchmark. But this is just for comparison competition, which is not a bad thing. Maybe we can do that. And it's a way for people to understand how good this algorithm that my vendor is selling me. But public data sets for training, I don't see it happening.
I just want to say I agree with his point. Commercial data, production data, no way.
That's for sure. I mean, that's something that sharing data. I mean, data that has a real commercial value is something that we won't see happening. What I was claiming is precisely for the way of validating the results and reproducing them, which is benchmarking, if you like. We want to make a reflection about unsupervised methods. I'm a little bit concerned that, again, deploying unsupervised methods in a running network is something that I don't see. I mean, frankly, I cannot imagine telling my operations guys, this will take control of the network and will learn by reinforcement and all the like. Oof, that's complicated, really. I mean, in the lab you can do this kind of experiments, but unless you can, to some extent, prove that the thing is going to behave.
Yeah, Diego, I think when I talk about unsupervised other things, it's just small for a particular problem. In our domain, the AI is very, distributed, right? So you don't have one methodology solving our problem. You take one problem that may be fraud detection, you develop certain methodology, it works well, it goes into production. We do have them in production. Call it whatever, supervised, not supervised, it just, you have to target one problem at a time. There is no one big blanket cover all. Yeah.
Jabber, Stanio asking, Senator Fernandez. I think it's beautiful. It's valuable to build data sets targeted to machine learning techniques. It's the most valuable thing to the community. He said it's impossible to train models without good data. And another suggestion would be organize competition similar to Kaggle, like this Kaggle competition online. And another research topic area from Molly. One area of research topic that we want to pursue is network intent. Use cases was mentioning, actual customer use cases would be useful.
Okay, we need to close the session because we have some already used additional minutes. But I want to emphasize one thing. We have nice discussions here. We would like to have these discussions in the mailing list as well. Because the mailing list is quite quiet. Of course, we try to provoke these discussions on the mailing list, but your opinions are quite important over there. Not only because the discussion itself, but it helps us to define the roadmaps. Okay.
Thank you all, and we keep on discussing this on the mailing list of the IDNet and Nmrg, please. Thank you.